So welcome to my talk on the microservice architecture. And really, the goal is to talk about, how the microservice architecture is enabling rapid, reliable, frequent, and sustainable software development, which, as Yara pointed out, is, in this whole context of digital transformation, is a really important goal for IT today. So I'm going to talk about the trends driving the adoption of microservices, talk about the essential characteristics of a microservice, talk about benefits and drawbacks. And then, one of the key thoughts I want to leave you all with is that, contrary to what you might have read on Twitter, neither monoliths or microservices are the future, right? Both those architectural styles are patterns, and which pattern you should use really depends on your particular context. So you have to understand the problems that you're solving and then pick the architecture that is the best fit. And that's a really important takeaway from this presentation. Before I talk about microservices, a little bit about myself. I've done a number of things over the years. Started off building Lisp systems, eventually ended up programming in Java, late 90s, started playing around with Amazon EC2 back in 2007. That led to the creation of the original Cloud Foundry, which was a PaaS for deploying Java applications on EC2. That then got acquired by SpringSource and then by VMware. And that's where the name, not the technology, but the name of today's pivotal Cloud Foundry comes from. So then for the past 7 years, I've been pretty much focused on the microservice architecture. I like to say that I travel around the world helping organizations adopt microservices through consulting and training, though at the present time, not so much travel, having to do it remotely. Of course, I have a startup, Eventuate. We're creating a platform for tackling distributed data management issues in a microservice architecture. I have my book, Microservices Patterns. And then, as part of the whole transition caused by COVID, I've started offering online boot camps. And you can learn more about this if you go to my website, microservices.io. And then if you want to know more, you want to get the slides, and sort of more information about the topic I'm going to cover, as well as enter a raffle and get discounts to my books and training classes, please just go to this bit.ly URL, TDC-2020-MSA. And I'll show that URL again at the end. So the agenda is, I'm going to start off by talking about what's driving the adoption of microservices. And that's all around needing to deliver software rapidly. It's also around developing applications that are long-lived. And then I'm going to talk about the monolithic architecture and why it's not an anti-pattern, but in some contexts, it's not the best approach. And then I'm going to talk about the microservice architecture, talk about the essential characteristics, talk about benefits and drawbacks. And then I'm going to finish by covering one of the key concepts in a microservice architecture, namely loosely coupled services. So I'm going to talk about what that means and how you can achieve it. So let's get going. Let's talk about why microservices, why now? And it all does go back to this whole digital transformation that's sort of, causing a big change in IT. So back in 2011, Mark Andreessen said that software is eating the world. What that really means is it doesn't matter what industry or business you're in, underlying the products and services that you offer is software. So it doesn't matter if you're an airline or mining or banking or so on, software plays a huge role in how you deliver those products and services. So, it really is about software. So in other words, every company needs to become an expert at delivering software. But then there's another factor, and that's really the fact that the marketplace within which companies operate is becoming increasingly volatile, uncertain, complex, and ambiguous. So there's constant change. New competitors are emerging out of nowhere. And that means that companies need to be extremely agile and nimble and able to respond in a rapid way in order to survive. It's funny, if you'd asked me 6 months ago, I would have given examples about how, financial service industries, companies risk disruption from virtual banks, and insurance companies that are oriented towards the gig economy, and so on. But I think today, if you look at the epidemic or pandemic that's affecting the world, that's hugely disruptive. It's not only is it taking a human toll, but it's actually transforming a lot of businesses. One example of that is certainly in the US. Online food delivery has basically jumped ahead 5 years, or online grocery delivery, I should say. That's jumped ahead 5 years, and that creates a massive challenge for IT, and that's impacting many other businesses as well. They're having to rapidly adopt. So the ability to emerge to the changes in the environment is essential to the survival of businesses. So businesses need to be agile and innovate much more rapidly. And because products and services are powered by software, IT must be able to deliver software much more rapidly, much more frequently, and much more reliably. And you can actually quantify that. It sounds like a fuzzy statement, but it turns out, based on research done by the authors of the Accelerate book, that you can quantify rapid, frequent, and reliable delivery with these 4 metrics. So this comes from DevOps. So there are velocity metrics, lead time. That's the time from a developer checking in a change to that change being deployed into production, right? You want to shorten that. There's also deployment frequency. How frequently are you pushing changes into production? So you can measure the speed, and then you can also measure the reliability. How quickly can you recover from a production outage? And then how often does a deployment cause a production outage? And obviously you want to minimize those 2 metrics. So it's all about going faster and faster, but doing it much more reliably. And that sounds kind of contradictory, but once again, the research shows that you can deliver software rapidly and you can do it reliably. This is some more research by the authors of Accelerate. They show that high-performing IT organizations are deploying multiple times per day. That also the corresponding lead time for changes is less than an hour. So in other words, I'm a developer, I'm sitting and I commit a change, push that change. Well, an hour later, that change is deployed into production. So there's a constant stream of small changes flowing very frequently into production. But it turns out that goes hand in hand with delivering software reliably. These high-performing organizations actually have fewer problems. Their whole software delivery machine is actually much more reliable. And the 2 really work hand in hand, which might seem counterintuitive. So something to think about, compared with how your organization is delivering software today. And another thing to keep in mind is the authors of Accelerate found out there's a strong correlation between high-performing IT organizations and organizational performance. So you do a better job at delivering software rapidly, frequently, and reliably, you make more money. So I like to think of what you need to do in order to deliver software rapidly, frequently, and reliably in terms of this success triangle. And there's 3 factors. You got to have the right process, you got to have the right organizational structure, and you need the right architecture. And the process that you should be following is DevOps, and I'll talk more about that in a minute. And the organizational structure you should have is these small, long-lived teams. So if we look at DevOps, right, that's a set of practices that enable where IT and basically all the different parts of IT collaborate to deliver software rapidly, frequently, and reliably. And there's these key practices, right? You've got a small cross-functional team that's committing changes frequently to a source code repository that's the source of truth for both code and configuration. That triggers an automated deployment pipeline that's fast and reliable. You know, that's important to achieve a short lead time. And then the changes are frequently deployed in a reliable fashion into your production environment. So that's the modern way of working. Not only that, another key idea in DevOps is this notion of hypothesis-driven development and also testing of alternatives in production. And the idea there is a requirement is a hypothesis. You know, it's an idea that if we do X, X will increase revenue. Turns out that that's often wrong. And you actually have to be able to quickly validate your requirements by making small changes into production, in production, and getting rapid feedback from real users. So in other words, you're constantly running experiments in production to validate what you think will make your customers happy. And it turns out that how much money you make is proportional to how frequently you can run experiments in production. So if you can only release once a quarter, that means you can run 4 experiments a year. So you got to wait 3 months or more to get feedback. Whereas if you're deploying many times a day, you're rapidly getting feedback on your requirements, and that leads to a much more successful business. From an organizational perspective, the idea is that you have a team of teams, right? And, you know, that's sort of the unit of scheduling. And these teams are small. Turns out that they should be roughly 5 to 9 people because that promotes trust. They should be long-lived because that also enables trust and it also promotes high performance. They should also be loosely coupled. They should be cross-functional, because that eliminates meetings and coordination between different departments. And then they should also own a piece of software, because that promotes long-term sustainable development. And that piece of software should be suitably sized so that it's not too large, that it overwhelms the cognitive capacity of the team. So it should fit in their heads collectively. And that's another key point. And a great example of this is Amazon. You know, they're so famous for their 2 pizza teams. And this coincidentally is an individual sized pizza that I ate in Japan 1 year and 2 days ago. So it's not the ideal pizza for a team. But, you know, or Amazon actually is structured as a network of loosely coupled small teams. And they actually are deploying, and obviously they're a very large organization, but even 5 years ago, they were able to deploy 130,000 times a day into production. So constant stream of small changes, and it's enabled them to dominate new industries as well, right? I mean, it's, you know, they're a phenomenally successful company. And that's all to do with embracing DevOps and small teams, and actually the microservice architecture as well. So what does this mean architecturally speaking? Well, once again, the authors of Accelerator found that, you know, people in these high-performing teams strongly agree with these statements. I can do my work without constantly communicating with people outside of my team. I can change the piece of software that I'm working on without having to ask other people to do work or creating work for other people. I can test locally, and I can independently deploy my software without coordinating with other people. And so these are key characteristics. So if you're working in an organization where you're constantly having to be in meetings to coordinate your work to get stuff done, here's something to think about. It turns out that these attributes of high-performing IT work are enabled by having the right architecture. You need a loosely coupled architecture, which is a function of Conway's law that I will talk about later. The ability to make changes to your software without impacting other teams is a function of modularity, where each module has an API that encapsulates those design decisions. Once you've hidden a design decision behind an API, you can change it without coordinating with other people. You also need an architecture that's testable if you want to be able to test locally on your laptop. And then if you can deploy independently, that means you have an architecture that's deployable. So we need a loosely coupled, modular, testable, and deployable architecture. So that's one big driver behind the idea of microservices. The other driver is this concept of having long-lived applications. So I'm sure many of you are working on applications that have been around for a long time. It's quite common to have applications that are 10 or 15 or years or even longer, which is actually a good thing. It's a sign of success. But the challenge that IT faces is that technology changes. You know, programming languages come and go. I mean, it's fantastic that, say, Java has been around for 25 years, right? And other languages have sort of appeared to gain in popularity, like Ruby on Rails, and then kind of declined somewhat, right? But then also within a particular technology, there's multiple versions, and those versions can represent significant changes. So there's constant evolution of technology. And it's really important to keep for the technology that you use to have its importance within your organization aligned with the importance in the marketplace. You don't want to be using obsolete technologies because they represent a whole bunch of risk. They're also impacting productivity. They make hiring difficult, and so on. So you want to have this constant alignment. And for a long-lived application, that means you actually need to be able to regularly upgrade its technology stack to keep it current, and which historically has been a problem, right? We've built these applications using, you know, 19 or 2001 technology, and 20 years later, we're still using 2001 technology. But that's not good. Right? It's not good for the organization. It's not good for the developers. So what you want to be able to do is have an application where you can incrementally upgrade it, right? You need, piece by piece, you need to swap out the old technology and put in new technology. That's really the only practical way of doing it, because a big bang rewrite to upgrade the technology stack is quite impractical. And it turns out that this is another form of modularity. It's where the API of a module actually encapsulates the implementation technology that module uses. So once again, because it's encapsulated, it means that it can be changed. And that's interesting, because usually the implementation technology sort of leaks out through an API. So to summarize, we actually need various architectural features in order to deliver software rapidly, frequently, and reliably and sustainably. We need a loosely coupled architecture. It needs to be modular, where the API encapsulates not only API or application level design decisions, but also the technology stack. It has to be testable, has to be deployable as well. So that's the kind of architecture that we need for modern applications. So let's look at the monolithic architecture, right? You know, it's a pattern that we've been using for a large number of years, and it's still a good one. So the examples in my book all use food to go. That's a food delivery application, right? Now, if you look at the structure of the application, so this was in my book, Pojos in Action, you know, logically it was layered, it was modular, but when it came to deploying it, everything just got packaged up as a WAR file. So there was a single deployment unit, and that's the monolithic architecture, where everything just gets packaged up as a single executable or a single deployable. And it talks to a single database. So there's the application talking to the database. And that's not necessarily a bad thing. Particularly when the monolith is small, it can be highly testable, highly deployable, maintainable, modular, and you can even upgrade it because it's not a huge amount of code, so it's quite practical to change it. The problem that you have is if you're successful, you don't stop development. you keep growing, you keep developing new features. And then also, if you're making money, you add more developers. So something that started off as a small team of 6 people developing a small application, give it a few years and you can end up with quite a large application. So it's growing and it's getting larger and larger. The rate of increase is also kind of getting fast, is increasing as well, right? It's a second order effect, which is great. You're successful. The problem that you have is that all of the desirable attributes that you need, maintainability, testability, deployability, and so on, tend to decline over time. So in other words, the pace of software delivery just gets slower and slower and slower. And this is a problem because it needs to be in order to compete in today's marketplace, it needs to be getting faster and faster and faster. So you're going in the wrong direction with your mission critical application that's powering your business. So this represents this gap between how fast you need to be delivering software and how fast you can deliver software actually can represent a threat to the business. You risk being disrupted by a fast-moving competitor or the world's events, right? Like today, I mean, I look at like online grocery stores, right, where overnight demand went through the roof and they needed to rapidly add new features to cope with that demand. Well, if you couldn't quickly deliver new features to deal with that change, you risked losing business to competitors. So a real challenge. And then, there's a bunch of technology sort of related challenges with monoliths as well. So one obvious point is there tends to be, like in Java, there is a single class path. So you might be able to have some form of modularity where you can build and test the order management module separately from the customer management module. But then when you put them together, there's not necessarily any guarantee that they work because they might have conflicting dependencies. So that's a challenge. So you tend, with these monolithic architectures, you tend to be stuck with the deployment, with the technology choices you made at the start of the project. And that can be a huge problem. There are just so many things that can't be changed. Your programming language, your application framework, or even just the version of a particular framework. It can just be too time consuming to upgrade because you have to upgrade everything. So huge problem. So collectively, right, you're delivering software quickly, you're using an obsolete technology stack, and so you end up in what I call monolithic hell, right? And while it's not inevitable, this does seem to be quite a common place for a lot of enterprise IT organizations to end up. Okay, so what's the alternative? Well, obviously, I'm here to talk about the microservice architecture. So let's look at how that fits with our architectural requirements. So first off, what is the microservice architecture? Well, it's an architectural style that structures an application as a set of services. So the services are highly maintainable and testable, since that's a key requirement. The lead time for a service, the time it takes from a commit to execute the automated deployment pipeline and be able to deploy it into production, right, should be very low, right? So if you're taking 2 days to test your service, something is not quite right. The services need to be loosely coupled. That's a key architectural requirement, right? Each service should be independently deployable, since that's a key goal. Each service should be owned by a small team, because that's another one of the requirements here, and I'll talk about that in a bit more in a minute. And also the services typically implement a business capability or a business function, and I'll talk more about that too. So if we look at the microservice architecture version of the food to go application, it could look something like this. You have a bunch of services, each one implementing a particular function of the business. Each service has its own database. That's important to ensure loose coupling, and I'll talk about that more in a minute. The services communicate primarily using asynchronous messaging. I mean, there is scope for using synchronous communication, but another key aspect of loose coupling is using asynchronous messaging instead of, say, REST. You can apply functional decomposition to the front end as well. So instead of one large web application implementing all of the pages, you have a different web app for each part of the UI. You can also implement an API gateway. So that's basically a service that defines the public API for your application, and then it routes requests accordingly. And in this example, there's JavaScript running in the browser and a mobile application that's invoking the API. So there's just sort of a vague kind of sense of what a microservice architecture should look like. And one thing to note is, well, there's a lot of boxes and lines here, right, which hints at one of the drawbacks of the microservice architecture, namely its complexity. There are just many more moving parts in this architecture. If we look at an individual service, you know, the reason for a service to exist, or in fact, the reason for a team to exist, is actually to provide an API, right? That's the whole point of the service. So that's the order, and this could be the order management API. An API consists of two parts. There are operations which can be invoked by clients. There are two types of operations: commands which change data, and then queries that retrieve data. So that's the operation part of the API. They can be invoked either synchronously using, say, REST, but they could also be invoked using asynchronous messaging. And I'll talk more about that in a minute. And then the other part of the API of a service are the events that the service emits. It's very useful, for reasons I'll talk about in a minute, for a service to publish events when its data changes. So if this was the order service, it could publish an order created event when an order was created. When an order shipped, it could publish an order shipped event, so on and so forth. And then a service has dependencies, right? So it can invoke the operations implemented by other services, and it can subscribe to their events as well. So that's what the building blocks of the microservice architecture look like. Oh, and yes, of course, the service has a database as well, but that's part of its private implementation. It's not sort of, it's really hidden behind an API. So we're sort of in this, which is an interesting switch for enterprise IT, which tends to be very database centric, right? You know, the microservice architecture is API centric, where the database is an implementation detail of a service. As I mentioned a minute ago, services tend to be organized to mirror business functions, right? So you think of a business as implementing a set of functions like order taking, kitchen management, delivery management, and accounting. So those different functional areas of the business would then map to services. So the order service, the delivery service, and so on. And if you're into business architecture, you can think of that you might use the term services implement business capabilities. Whereas if you're into domain-driven design, you can think of a service as implementing a subdomain or perhaps a bounded context. Depends on which sort of school of thought you're most used to. So, you know, and then the key issue is, well, how many services should I have, right? You know, that's sort of the key question when coming up with a microservice architecture. Given that the goal is team autonomy, you should really start off with just one service per team, because that enables the team to work independently while not introducing excessive complexity. So that's, you know, the one common anti-pattern is having very fine-grained architectures. Quite a few clients I visited have basically had like one service per developer. So I visited a company and they had 300 developers and 300 services. And that's just introduced, generally, that will just introduce unnecessary complexity into your application. So you should try and avoid that. Have coarser-grained services and minimize the complexity. But of course, sometimes you should have more services. So you might introduce more services if, say, if the team becomes too large, you want to split the team and split the service. Or if the deployment pipeline execution time is taking too long, you could split a service into 2 separate services that can be developed and tested independently. And so that, in that case, the team would own 2 services. There can also be some technical reasons for having multiple services. One common pattern that I've seen is where an organization has some machine learning data experts, right? And they've created a machine learning model that's implemented in Python, yet the rest of the organization is using Java. So perhaps then the team that's responsible for that particular business function would have a Java service that's implementing most of it, and then there would be a Python service that implements the machine learning, the fraud detection algorithm, for example. So that's a technical reason for needing multiple services. Another common technical reason for splitting is that some parts of the application can have very sort of stringent SLA requirements. So if you're processing credit card payments, for example, that API must have extremely high availability, whereas the API for letting a merchant maintain their account, obviously that's important, but it's not as important as being able to charge someone's credit card. So you might want to split based on that. I've also talked with organizations that have been in heavily regulated industries. Part of their application has to be highly regulated because it's dealing with medical data or credit card, say credit card payments, right? You might want to split that off from the parts of the software that aren't as regulated for easier development, and so on. So there's sort of various technical reasons or regulatory reasons why you might want to introduce additional services. So that's one key thing. But anyway, so that's sort of a brief overview of the microservice architecture. So the numerous benefits, right? It improves maintainability. Each service fits in the heads of the development team. It doesn't overwhelm them with complexity. It also preserves modularity because you've got this impermeable API, whether it's a REST API or a messaging API. Each service is easier to test because it's smaller. Each service, you can change the technology stack of each service independently, which really promotes long-term development. Each service, by definition, can be deployed independently. Each service can also be scaled independently, right? Whereas a monolith, you just have to run multiple copies of the monolith. You could have 10 instances of the order service, but only 3 instances of the customer service. And it can also improve fault isolation because, highly available functionality can be deployed as separate services on entirely separate infrastructure versus less critical, and separated from less critical services, which is running on a different set of infrastructure. So you've got proper fault isolation, which is really important in a lot of businesses. So numerous benefits. But by far, this slide really sums up the key benefits of the microservice architecture. It's basically giving you the testability and deployability and the modularity that you need, plus the loose coupling, in order to deliver software rapidly, frequently, reliably, and sustainably, right? You've got these teams each team is able to work independently. They're committing code to their own source code repositories, and that's triggering a build, which can automatically push that service into production. So they're working independently, say 80% of the time. And then it also lets you evolve your technology stack, right? You could have a bunch of Java services and then decide that you want to try out Golang, right? Not a problem. You just implement a service in Golang. If you like it, that's good. But if you don't, that's not a disaster, because you've invested a relatively small amount of time, building that service. And then at a later date, you decide, well, I like Kotlin more, so I could switch, replace my Golang service with Kotlin. So it lets you experiment safely with new technologies, occasionally fail, but overall you're able to incrementally evolve your technology stack, which means hopefully 20 years from now, people won't be stuck with 20-year-old technology. They will be able to constantly upgrade their application's technology stack. So there obviously are some drawbacks, right? So, you've got the complexity of development, right? You're building a distributed system. So you've got inter-process communication. You've got multiple databases, which transforms how you implement queries and transactions that span multiple services. Testing is simultaneously easier, but then you have to learn new patterns on how to ensure that that services work when put together. And then from a deployment perspective, you have, instead of one application in production, you effectively have tens or hundreds of much smaller applications. So there's many more moving parts that need to be monitored and managed and orchestrated and so on. The good news is that there are technologies, there are patterns, there are techniques that for solving all of these problems. So there's, for instance, consumer-driven contract testing for making service, for doing kind of integration style testing. You've got deployment platforms like Kubernetes that automate the deployment. And there are frameworks like my own for Eventuate for dealing with distributed data. So there are ways to tackle this complexity. There are some hard challenges, like correctly identifying service boundaries. That's sort of, that's purely a sort of thought exercise that technology can't really help you with, right? So it requires you to have good architectural and design skills. So that's a challenge, and also refactoring a monolith to a microservice architecture. It's actually quite a challenging process. For example, Airbnb, I think they started back in 2015, so 5 years ago, refactoring their Ruby on Rails monolith to a modern microservices architecture. And I believe that they're mostly done, but they've still got more work to do. So a very long journey. But in general, so if you are developing a long-lived application that's large, it's complex, there's a lot of people, and you need to deliver it rapidly, frequently, and reliably, then the microservice architecture is often a good choice, right? And I'm not saying it's definitely the right thing to do. I mean, as an architect, you have to carefully, evaluate the context, figure out what you're trying to build and the structure of the team, and decide, should I use a monolith? Should I use microservices? So it's not one or the other, and it's really one of those it depends type issues. Okay, so I got a few more minutes left, and I want to finish up with talking about one key topic, which is namely this issue of loose coupling. I'm sure many of you have heard about Conway's law. And I forget when this law was sort of written down, but I think it was 40, 50 years ago, quite a while, right? And he wrote that basically the architecture of an application mirrors the structure of the organization that created it. So his classic example is, if you're building a compiler and there's 3 teams, you will get a 3-phase compiler, right? And sort of one implication of Conway's law is that if you want your teams to be loosely coupled, then you need to have a loosely coupled architecture. And that's sort of a really critical point. And interestingly, even though this law is from quite a long time ago, Mel Conway actually has a Twitter account, and he has some really interesting things to tweet. So go follow him. So I want to talk about this concept of coupling. So it's quite normal for services to collaborate, for one service to invoke the API somehow of another service. So perhaps, in the example I use is the order service, before it creates an order, has to verify that there's sufficient credit available for that customer. So somehow it has to reserve credit in the customer service. So some kind of dependency, some kind of coupling is inevitable, but you want to ensure that the coupling is loose. So it's loose coupling between your services. And it's like, well, what does that mean? It turns out there's actually at least 2 different types of coupling. So there's runtime coupling, which is where a service can't respond to a synchronous request until it gets back a response from some other service. So you can imagine a bunch of services communicating through HTTP. That actually is, you end up with tight runtime coupling. But then there's also design time coupling, which is where a change to one service, like the customer service, forces updates to other services that use it, like the order service. And that's design time coupling. And primarily Conway's law actually applies to design time coupling. He wasn't talking about runtime coupling. And the problem you have with tight design time coupling is that it requires teams to coordinate, right? I want to make a change to my service, which changes the API in some incompatible way. Well, I now have to go talk to the other teams that are going to be whose services are going to be impacted by that change. So it means you got to have meetings, right? It means you got to find a meeting room, which globally seems to be a problem, or at least prior to us all working from home. And that really slows down development. Studies have found that decision-making between teams takes 10 times longer than decision-making within teams. So it's really important to kind of minimize that kind of coupling. And your services want to have well-designed, stable APIs that basically evolve in backwards compatible ways. And you also have to be careful with shared libraries as well, which I'll talk a little bit. So you want to have services that I say should look like icebergs. So they should have a relatively small API that hides a complex, a much larger implementation. And the idea there is that what is hidden behind the API can be changed, the API easily, right? Whereas if the API itself changes, then that impacts the clients. So you want to have services that look like this. And great examples of this, right, is you think about Stripe, the payment service. I know their API is a bit more complicated than that, but one of their key operations is charge this credit card, right? Really simple operation that's very stable, doesn't change, yet the complexity behind that is huge, right? It's a $1 billion company. So that's a great example of encapsulation. Or Twilio for sending an SMS. Send this text message to this number, right? Behind that, there's a massive amount of complexity around doing that globally. But they hide that. So you want to have that mindset when you're designing your services. You also want to avoid shared libraries that contain business logic that can change, because if you have a library that implements a business rule, and that business rule changes, all of the services that include that library need to be changed in lockstep to prevent bugs. And there was a recent talk at QCon, which was like how by segment, which was how we failed at microservices. And the fundamental issue that they had, I believe, was that they ignored this notion of coupling and had a shared library that multiple services used. So that's the problem. You also want to avoid shared database tables because that results in design time coupling as well. I can't change my schema without talking to all of the other people whose services access that schema. So that's a problem. And then I'm just going to spend a couple more minutes talking about runtime coupling. This is the other type of coupling that impacts availability. So imagine this simple design where a post request comes into the order service, which makes a put request to the customer service to reserve credit. The order service is waiting for a response to come back. And then when it gets one, it can respond to its client. Super simple design, but you think about it, the order service can't respond to a post request unless the customer service is available. So the availability of that operation is the product of the availabilities of the two services. And this is sort of a consequence of this anti-pattern where you think that you just think that distributed communication is free. But it's not. It introduces it results in high latency, and the availability of an operation is basically the product of the services that are synchronously invoked when handling that request. And I visited clients where like a key operation in their API was like invoking 10 other services, where there was a risk of high latency and low availability. So they were really at risk of violating their SLA. So a key idea here is that you want to have these self-contained services that can handle a synchronous request without waiting for a response from another service. So that's kind of a key design pattern. One way to achieve that, which is to actually avoid the problem by merging services together. So putting the customer management logic inside the order service, which, kind of sometimes you should do that, but it's against the idea of microservices because, it actually works, it reduces availability, but it means you have larger services and larger teams. So that's not a good approach. So what instead is you want to rely on asynchronous messaging between services, right? Great book for this is Enterprise Integration Patterns, where services are communicating via a message system over these message channels to recipients. And there's a couple of different ways that you can do this. So one alternative design is to use what's known as a saga, which is a whole other presentation in its own right. And here, the order service handles the post request by basically creating an order in a pending state and initiating what's known as the saga, and it returns a result to its client immediately, saying, I've created the order, check back later to see whether it was approved or not. And then the service communicates with the customer service by exchanging events. This is actually what's known as a choreography-based saga, and one of the topics in my course. And the nice thing about this, right, is that it improves availability. The order service can respond to order requests without talking to any other services. The downside is you've got this more complex event-based mechanism, and also the response doesn't tell the client whether the order was approved or not. It has to check back later. But this can be extremely useful way of decoupling your services. And then the last slide is another possibility is to use another event-based approach known as CQRS command query responsibility segregation, where data is replicated to where it's needed. So in this case, the customer's credit limit is replicated to the order service, which then instead maintains the available credit itself instead of maintaining the available credit in the customer service. This enables the order service to respond to order requests without having to then go and talk to the customer service. So by moving the data to where it's needed, we've made this service self-contained, which improves availability, and also it simplifies the API. The response can actually tell the client whether the order was approved or not. So, some quite interesting but complex patterns that rely on asynchronous messaging between the services. But these are really important patterns that you need to use when architecting, a microservices-based application if you want it to be highly available and have a relatively low latency. And I should say there's one of the downsides is the cost and the complexity of replication. So, if you're replicating a massive amount of customer data, maybe this is too expensive, but depends, once again, on your context. So in summary, right, that's my talk. Monoliths are not the future. They're a pattern. Microservices are not a best practice. They're a pattern. And which one you should use depends on the context. And as an architect, it's your job to just choose the most appropriate architecture for a given application, right? I've already talked about how services, the microservice architecture is an architectural style that structures an application as a set of services, right? And it basically, it's an architectural style that enables you to deliver changes to long-lived applications rapidly, frequently, and reliably. So that's my talk. Thank you for listening. Hopefully someone is listening. I can't see. And I hope that you found it useful. And once again, please go to this link to sign up to get more information. So thank you so much.